people that did answer that they will attend. So now it has officially started. So what's today's topic? Today's topic is it's one of those things that we need to talk in the manufacturing environment or supply chain, but that we rarely touch on because we take it as a given. That is the data we collect or the quality of the data that we manage through our whole analysis. So today we are going to take something called the Google method that is used for data science and apply it to collecting data in manufacturing. I've been on both sides of the house as a data analyst, also doing the functions of a data analyst and working in manufacturing. And I have come to the realization that we need to better control the way we create data or we analyze data in our facilities. So for some of you that don't know me, my name is Artemio Alanes. I have a mechatronics engineering degree from the University Autónoma de Nuevo León from Mexico and a master's in science from the Rio Grande Valley, the University of Texas, Rio Grande Valley. My whole work experience has been rotating around the medical industry, first as a process engineer, then as a transfer engineer, and currently as a project manager for the supply chain side of the house for Fresenius Medical Care. I also started in 2019 this type of webinars, workshops that talk about just statistics and how can we improve and do a better job of doing analysis. So Google method is really simple, guys. Most of us that work in the manufacturing environment know that there are methodologies pertinent to lean manufacturing, Six Sigma that we can follow that can help us analyze. But there's also the Google method. Google method is more based on data. So you see here on your screen that there's 6 steps. For the manufacturing environment, we are going to take into account 5 of them. The first one is going to be ask. Second one is going to be prepare. Then process, analyze, and share. Now, you can look at a lot of documentation online that can give you a lot more specifics of each of these steps, but they're going to be based on more of a data science point of view. The point of view that I'm going to give you today is, what do we do in the manufacturing environment? Sometimes we don't have the data. Sometimes we don't even know what we're going to analyze. We were just told to do the analysis and that was it. So the first step, like every lean manufacturing, Six Sigma, and this, we got to ask, right? We got to define what the hell do we want to do with the analysis? What have we been tasked to do? So when we start doing an analysis, this is the first email you get in the morning when they ask you to start validating, verifying, working in manufacturing, gather data. First of all and foremost, we have to understand, or at least get into the broad picture of what we want to achieve with that analysis. Now, for those who work in the manufacturing environment and supply chain, I might say, well, that's a given. It depends, right? So what do I mean by this? If we want to do a comparison, if we want to compare product A to product B, then we know that the data that we have to get, depending on the scale, has to have a lot of resolution, or at least some degree of resolution. And we can also understand that we need to have comprehensible amount of data to be representative. But first is, what do we want to achieve? That's really important. Just give me a second. There we go. Just muted someone. So again, what do we want to achieve? Do we want to do a characterization? Do you want to validate or verify? Do you want to do a comparison? Do you want to determine something or reach a conclusion? Do you want to optimize? Do you want to reduce a process? Do you want to maximize it? We got to get it, write it down somewhere. What do we want to achieve? And I have seen a lot of engineers skip that step, do a lot of work, and at the end, they come up really, really short. Next step, we got to ask. Now we got to start preparing. And there's two questions we got to answer here when we want to prepare to do an analysis. One of them is where the information is coming from. Now, most of us, we say, well, it's coming from the manufacturing environment, or it's coming manufacturing process, or a molding procedure, or a molding process, or a stamping, or it's a painting process. We got to understand where the data is coming from. Why? Well, because later on we're gonna take a little bit of time to discuss the quality of data. Is that data or that information that we are gonna acquire relevant to what we want to analyze? If they ask you to go measure the weight or compare the weight of a product, you're not going to measure the length, right? Now, if you have various sources of data, being one of them being a database that comes straight from the scale, the other one might be someone writing in a spreadsheet the data that they saw on the scale. Do you want to take the data from the database or from the format, or are you going to ask around what the operators or the quality managers or the quality technicians have seen on the field? So we got to be very, very careful to analyze where the data is coming from. The other thing we have to do to prepare is what are the inputs and the outputs. Every process, regardless of if it's a service or a physical product, has inputs and outputs. Heat, it could be heat, temperature, pressure. It could be idle times. It could be number of calls on weight. It could be types of or categories of different assessment a person has to carry out with a customer. Could be a number of products on the shelf. It could be a various things, but we have to make an assumption. What are the inputs and what are the outputs? Now that we have those both questions solved, we got to ask ourselves again, where's the data coming from? And in the manufacturing environment, there are three main points or houses where we can get data from. One of them are databases, and these are, for a better expression of the term, just databases. SAP, Oracle, BPEX, you name it. Any database you can pull data from. The other one is post-problem definition collection. What that means that once you define the problem, you know your inputs, you know your outputs, you know where you're going to get the data from, you have to go collect it. You got to go stand on the line, stand with the process, and start writing down in a little clipboard. Observation 1, this is what I got. Observation 2, this is what I got. And there's also historical data. Now, there are some pros and some cons to each one. Databases, the pro is the data is just there. The con is it's really hard to get sometimes, unless you know query or you have integrations into your software to actually pull that data from that database. But again, it's a lot of data. Also, it's a very good way to get a lot of information. Post-problem definition and collection. What's the deal with that one? Well, first of all, the pros is the information is really, really clean. What does that mean? Since you're building not only a process, you're not analyzing a process, you are also doing or setting up the standard procedure to collect that information. And you control it. The cons to all this is that it's very expensive for you to do, because it's going to take your time and time away from the machine or on the machine. to collect that data. Historical data is sort of like a database, but it's more referring to stuff or the data points or the information that's on physical records. And the pros for that is that the information is almost as clean. It's usable. There's a lot of information, but the con to it is that sometimes it gets recorded with a lot of outliers, or it has a lot of mistakes that don't get validated if they're right or wrong. They just get thrown into the mix, right? Now, how can I do a strategy? If I'm tasked to do an analysis and I have to collect the data, what are my available tools? First of all, the first one that we have, or any one of us have executed, is an observation or a check sheet. Another form is to recollect historical data. One of the plus or the pros also of this is that since it's under an SOP, historical data is very reliable. Semi-clean, but reliable. It also they can be done by filling out forms and one-on-one interviews. Now, after you prepare, after we answer the questions, where is the information coming from, or the data? What are the inputs and what are the outputs? We measure if we're going to get it from a database, we're going to do a collection of data points or information after the problem is defined, or are we going to use historical data? This is the step that we always miss, guys, which is auditing our data. And what does that mean? The guys, all the people that have worked with quality audit, the quality departments, when they hear audit, it's a scary word, right? Because that means people are going to start checking for any single detail. Now, we have to have that same mentality when we're analyzing the data that we're using. Now, what does audit the data mean? Well, we got to answer two different questions. One of them, does the data make sense? If you're measuring a box or weighing a box that's supposed to be 50 pounds, if you look at a historical record and it says 5,000 pounds, that means someone wrote it wrong. If you're measuring a piece that's supposed to be 49 inches and someone wrote down 4.9, that's a keying error. Does it make sense? So after we look at all the data points that do not make sense, we got to look at the stats and we got to analyze if the stats make sense. What do I mean? Let's say, guys, you are collecting or you ask someone, a quality tech or manufacturing operator, to collect the times of an assembly line. And you start collecting the times, you get 30 data points, you take the mean and you take the standard deviation, and it turns out that half or a little bit less than half of the distribution is below zero, and you're taking seconds in time. So can you have negative seconds in a manufacturing process? Well, if anyone could do that, that would be wonderful, because that would drop costs and production times instantly. But if we get data points like that, well, they don't make any sense. The stats don't make any sense. Now, what are some common findings or errors that we find during this audit? First of all, what we got to look out for is, one of them is keying errors, right? That's the one that I mentioned. If the measurement is supposed to be 49 and you wrote down 4.9, or the measurement is supposed to be 50 and now it's 500, but that's a keying error, right? And it's going to pop up in the statistics and in your distribution, in your box plot, in your graph and your trend lines. That's the first one we got to look for. The second one is non-reproducible errors. So this means that if, let's say, you have an outlier in your data, if you're a quality representative, if you've been working for a lot of time in the manufacturing industry, you understand if you have an outlier, the first question that pops into your mind, or the first action that you think of, and it's it's not supposed to be done, but we still think it, is to remove that data point. But we gotta ask ourselves, is this data point part of the process? Can I reproduce it or not? If you can reproduce it and you can set controls in place, you can take it out. But if you can't, you gotta leave it in, right? And the third highest common error that I've seen in in collecting data is you got the wrong manufacturing process, the wrong measuring process, or the wrong equipment to measure it. Let's say you want to measure the length of a tube that's supposed to be 10 centimeters plus or minus 5 millimeters. And you give your quality technicians a ruler that measures in centimeters with no millimeters. Well, right there, he's not going to be able to measure accurately that dimension or the length of the tubing. And that's one of the common errors. So keying errors, non-reproducible errors, and wrong measurement errors. Now, there are some data and data packages or data software that you can use to validate your data. But these are my three go-to tools when I look at a lot of data. The first one is descriptive stats. What does the mean say? What does the standard deviation? What does the Q's mean? The mean, the mode. We just look at what it says. Then we have a statistical process control. And that's pretty straightforward. Statistical process control, a bunch of data. It's a really healthy, fast way to tell us if we have a problem. Second one is histograms. Histograms are going to tell us tell the distribution that the data is going to follow, and if it makes sense. Again, I'll go back to the example of the minus 1 seconds, minus 2 seconds in a manufacturing environment. If you have an histogram and you're measuring time, and part of that distribution goes into the negatives, well, that means that you're not accurately assessing the distribution, which can really hurt your capabilities in your manufacturing or service environment. The other one that's pretty straightforward is the box plot, and that's one of my favorites. Why? Well, it's easy to understand, very easy to understand, and upper management is used to seeing this type of graphs, and very easy to convey an idea with this type of graphs. Okay, now, after we ask the questions, after we prepare, and after we process or validate the data, we have a clean data set. We are ready to go. We can start analyzing. Now, there are three steps that I follow to do a proper analysis of any data or any data set that I come across. One of them is, am I choosing the right distribution? Sometimes saying that the mean or the standard deviation represent the whole data set or the whole population or the whole process, that means that evaluating a process by just looking at the mean might not be the right choice. Might not be the mean, might be the median, or the best choice might be a mode or another parameter that belongs to another distribution. Now we got to understand to ask ourselves to choose the right analysis. Why? Well, in all of our stat courses during college and high school, everything that we learned was I want to say it like case sensitive. That means everything is done taking into account that the data follows a normal distribution, which is a norm, mean, and a standard deviation. So we got to choose very carefully, because that is going to move our data points or an analysis or our results. And the third one is to just let the results speak for themselves, interpret them. At the beginning, we made a hypothesis unwillingly. We always do a hypothesis, but now we gotta let the data talk. Most of us as engineers, we stop here. We just interpret the results, do a small snippet, stick it on a piece of paper, write up a report, a couple of lines, and hand it in. But there are more things, or there's an extra step that we can do that's going to push us forward to the forefront of every other engineer, every other analyst that we have in the company, and that's this. This is short for visualization. And that's where we gotta read the room, guys. Read the room it's an expression. If any one of you has ever heard it, read the room is we gotta share the information in a format that the people who are going to receive it are going to better understand it. So let's say you're doing an analysis for, again, I'm gonna do time it takes to manufacture a specific piece. So if you're writing a technical report, a histogram, a median, a histogram, the mean and the standard deviation in one report might be sufficient. Let's say that report is now being handed over to finance. Finance might not care about the distribution. They might care more about the minimum or the maximum of the time you're going to take to calculate the cost of the product. Now, if you hand it over to quality, they might not like to see the histogram. They just want to know what are the defective parts per million you're going to be producing, so they can start building a sampling plan based on that. So you got to read the room. You got to understand. Or if you're speaking to upper management, maybe a histogram might be a little bit more confusing, and a box plot would be a lot better for them to see. So again, guys, you gotta read the room. So let's sum up what we seen today. The Google method. First of all, we gotta ask. We gotta determine what the hell we're doing and why we're doing it. Prepare. We have to know where the information we're going to analyze is coming from, or if we're going to get it, collect it, and what are the inputs and the outputs to the process. After we collected all the data, we got to audit it. We got to ask ourselves, does the data make sense? And does the statistics or the stats make sense as well? We got to look out for errors in that data. If there are errors and we can reproduce them or we can justify them, you can safely take them away, delete them from the data set. Some of the tools is descriptive stats, SPC, histograms, and my go-to, which is the box plots. And then we can start doing the real work, which is analyzing and preparing a presentation or a visualization that's adequate for the room or the end reviewer of the report that we're building. So guys, it was a very, very short workshop, but I wanted for you guys to understand that we don't just go out there and measure and compare and do an analysis, compare, and then stick it in a report and that's it. Sometimes we have to do some pre-work. We have to not only understand the process, but understand the data and why we're collecting it. Sometimes it doesn't make sense. Sometimes there's an easier way. a cheaper way, or it makes more sense to collect more or less data depending on the needs of the analysis. So at this point, I am going to stop the recording